All right, guys, hopefully you had some good luck with the simplifying trig expressions. You might see that in the book, it talks about verifying or proving trig expressions. We are not going to be doing that this year. We will be out of time. Plus, it's just something it's really hard to kind of give you a vision. I mean, I can work problems, but unless you can ask a lot of questions, and anyway, we're having to cut some things out in the whole coronavirus experiment, and that's one of the things that got chopped. Now, we will cover it again next year if you're in a regular pre-cal or a math team pre-cal class. Both of those will cover it again. So good for you. You don't have to learn it this year, but it is one of the trickier things. It's kind of a love-hate relationship with my students. They either love it or they hate it. Not both, though. But anyway, we're going to forego that. Also, today we're going to start talking about how to use a new grouping of identities called, some people call them the alpha plus beta or alpha minus beta identities. Some people call them the addition identities. Some people call them the sum or the difference identities. But we're going to take a look at those. Now, in your book, and I'll refer back to this again, there's a proof on how to prove the cosine of alpha. I think it's alpha plus or maybe alpha minus beta. I'm not going to go through the proofs. Again, it's one of those things. I have included them in the book. You can look at it. I will go over them again in pre-cal, so you'll see it. But it just gives you an idea of where this comes from, and that it's not just magic that's occurring. So if you want to look at those, I'll refer to those later in this video, what page it is, and you can go back. And then also there's another proof with a lady who has real big bug eyes. There's another set of little hints on what to do when you're proving identities. We're not going to be proving identities like we are simplifying identities. So you don't really have to follow that list. But again, that's something we'll do next year. And then one last thing, there was a worksheet in your book that had classwork simplifying identities. I chose to do if you remember a few days ago, I chose to do some of the even problems in the book. So I skipped over that and just did some of the even problems in the video for practice. So don't worry about completing that. I don't even have the key posted on Schoology, so don't worry about that. So anyway, we're going to jump into the sine, cosine, and tangent, alpha plus beta and alpha minus beta identities, the addition, subtraction, or the sum and difference identities. Take a look at how they work. Take a look at what we can do with them. And I think that you'll see, I don't know if they're cool or whatever, but I don't think they're too much trouble, and I think you'll be okay. All right, let's check it out. All right, here you go. Lame dad joke of the day. Why do you never see elephants hiding in trees? Because they're so good at it. All right, so like I mentioned a second ago, there's a proof in your book. It's in the book on page 39. I think there's actually a version of the book of proof in your textbook as well. But it's a way, basically this has a value. A lot of people look at this cosine of alpha minus beta, and they think, oh, I can just distribute the cosine in and get cosine alpha minus cosine beta. And that is absolutely terrible. And the reason why is, remember, the distributive property works when you have a number out front, right? Or a variable that stands for a number. So if this had been like 5 times alpha minus beta, then yeah, you can distribute a 5 in, but the cosine's not a number, it's a function. Basically, remember, cosine's saying, what is the adjacent over the hypotenuse of this angle? The angle formed by subtracting those two angles. Well, I have no idea. I don't even know what the two angles is, but this right here is equal to something, and this proof I'm giving you on this page explains it. Now, you can read it. If you are pretty good at reading through math material, it should make sense. But I guess the point I'm trying to make is it's pretty ugly proof. You can see all this, right? So I'm not going to make you know all this, but when you finally get down to the end, you can see that this cosine of alpha plus beta is equal to that, right? So this is like a cosine of two angles added together is equal to the cosine of the first one times the cosine of the second minus the sine of the first times the sine of the second. And that has nothing to do with distributing the cosine in, does it? Okay? And then if you turn over to the next page, but you do not have to know this proof, all right? If you turn over to the next page on page 40, it shows you how to get the alpha plus beta. It shows you how to get the alpha plus beta for sine, shows you how to get it for tangent. And then if you can do the alpha plus betas and the alpha minus betas, and by the way, I'm going to go back to this first page. This got down to the cosine of alpha minus beta. That's the formula for cosine alpha. And then I made a substitution to get the one for the cosine of alpha minus beta. I made a substitution to get the formula for the alpha plus beta. So basically it looks like whenever I'm doing a cosine of two angles being subtracted or added, I do cosine first, cosine second, cosine first, cosine second, and then sine first, sine second, sine first, sine second. And then it looks like the sine, the SIGN, changes in the middle. So if it's minus there, it's plus there. If it's plus there, it's minus there. Now, for you guys, you're not even going to have to memorize that because it's open notes quizzes this year. But you're going to have them memorized by next year. So I would encourage you to really try to get them memorized. It'll make your life much easier next year when I'm expecting you to know them. You won't have to work as hard. And then on the next page, I was referring to this, to find the sine of alpha plus beta. I can find that through some clever manipulation. Again, you don't need to know these proofs. And I turn out to get this sine of alpha plus beta formula. And again, I'll show you all these proofs next year and talk about the why. What's important to you is to know that the sine formula right there for two angles added or the sine angle for two angles subtracted, of course, it's not the same as cosine. You know, remember the cosine one went cosine, cosine, sine, sine. This one goes sine of the first, cosine of the second, and then cosine of the first angle, sine of the second, and we keep the same plus sign or same minus sign. All right? So they're a totally different way to do the functions, but there's kind of the proof if you were interested. And for the tangent, the proof on the tangent actually is not so bad. You know that tangent's defined as sine over cosine? Well, that would mean that tangent of alpha plus beta is defined as sine of alpha plus beta over cosine of alpha plus beta. And if I wrote down the two identities, the one for sine and the one for cosine, and did this clever algebra right here, you end up getting spit out this tangent identity. And the tangent identity, ironically, kind of looks like you're distributing tangent in there. Tangent alpha plus tangent beta in the numerator. But then in the denominator, you go 1 minus the tangent of each angle. And you'll notice if it's plus there, it's plus over minus. But if it's minus there, it's minus over plus. So those are your three trig of alpha plus beta or alpha minus beta formulas. I guess 6 because there's a plus and a minus for each one. We are not going to learn special ones for secant and cotangent. And the reason why is all I have to do is go flip these. Like if I want a cotangent one, I'll just take the tangent one and flip it upside down, right? Because they're reciprocals. If I want the cosecant one, I'll just put all of this on the bottom with a 1 on the top, and that'll become a cosecant one. So I don't bother memorizing or learning any of the other ones, just the 6 that we've just talked about, okay? So you're not gonna have to, again, on your quizzes, you'll have your identities page, you won't have to worry about it. And then to just mention a couple other things, there's another sheet, it says examples of questions that were gonna be on the quiz tomorrow. Keep in mind that I printed all this not knowing that the coronavirus is gonna shut the world down. So again, yes, you might need to know how to do all of these, and hopefully you can, but you're gonna have your identities sitting in front of you, all right? So these are just examples of fundamental identities that are on there that you could do. Like for instance, remember this one, the cosine of the negative angle? Remember with cosine and with secant, because they're even, you can basically just throw the negative away and write cosine of u. Or remember this one, do you remember the Pythagorean identity that's tangent squared theta plus 1 equals secant squared theta? Or do you remember that cotangent is the reciprocal of tangent, so 1 over tangent theta? Right? These are the kinds of things that I'm just putting out here. Or do you remember that cotangent of negative u, because that's one of the odd ones, I can factor the negative out and call it negative cotangent of u? Or do you remember that the co-function identities, that the cotangent of 20 is the tangent of 90 minus 20, or 70? Or do you remember this Pythagorean, a sine squared of an angle plus the cosine squared of an angle, no matter what the angle is, as long as they match, always equal to 1? Or even this one that I just taught you. This is actually the tangent of the alpha minus beta, tangent parentheses alpha minus beta identity. But most of these will be pretty easy for you to do because you've seen all this stuff. Because you'll have the identities sitting in front of you. You don't even have to have them memorized. So anyway, that's on your sheet. I wanted to just mention that. Also, I've made mention that you have a trig identities page. These are the identities that you're going to have to know on the front of this. These are what we call the fundamental identities. Those are the trig functions you learned. Those are the reciprocal identities we've been using a ton. That's the tangent, cotangent, quotient identities. We've been using those a ton. And then remember the co-function, sine and cosine, cotangent and tangent, secant and cosecant. Those are those 90 minus theta identities. Hopefully we know those. Those are the three basic Pythagorean identities, although we can move stuff around and use them different ways. And then those are the even and odd identities. And remember, the only two evens are cosine and secant. That's where the negative gets thrown out. The other four, the negative gets factored out. And then what we're getting to next, and today we're going to talk about how to use those, are the addition formulas or the sum and difference identities. Okay? So those are these, and not quite sure why I'm missing a comma there. Oh well. But anyway, these are the 6 identities, the 2 for sine, 2 for cosine, and 2 for tangent. Again, I really want you to have these memorized. You will have to have them memorized eventually, but you can take this identities page into your test with you. It's going to help you a little bit. Most of my kids always know these by the time test comes around, but we've had lots of quizzes on them. But here are the 6 we're going to use today in the applications that we'll have. So the best way to kind of show you, I think, is just to kind of work through some of these, and I've got some classwork for you. Oh, before I get to that, I want to just reference, I was referencing my simplifying trig expressions. This is on your page 45. Remember those 7 or 8 rules I mentioned that have Kevin Hart down there at the bottom? Never just stare at it and do nothing. Do something. But if you get stuck, try these 7 rules that I've mentioned here. And it usually can help you get going on simplifying these expressions. And then on the back of that page, it says rules for verifying or proving. But that's what I just told you we were going to ignore this year. We're going to pick back up on it next year. But we're not going to get to this, sadly. But something has to go based on the pace that they are making me move with you guys. So you can ignore that page, and we are going to jump, therefore, to page 47. So if you can pull out page 47 with me or pause while you do, I will give you a moment to get it. Page 47 is where we're going to pick up today. And I'm going to zoom in a little bit. Actually, we're not on page 47. Page 47 is the thing I told you in my little introduction that I skipped these problems because I was just working on book problems. So we're going to skip over that 47 and we're going to move, and 48, we're going to move to page 49. Sorry again about all that. All right, so here we go. This is the sum and difference identities. So everything I do today, I will be using these alpha minus beta and alpha plus beta identities that we have just learned. Okay, so if you want to get that page and have it handy as you're looking at this so you don't make any careless errors with these, that's not a terrible idea. But anyway, we're just going to go through these and see what we can do. Okay, so the first one that I want to look at is this number 1. Again, I'm going to zoom in a little bit on this. And it says it wants me to simplify cosine of 120 minus 45. Now, by the way, a lot of people would look at this and say, oh, cotangent of 120 minus 45. I can just subtract those two numbers, and when I do, I get cosine of 75. And that's right. But the problem is you're not going to have a calculator on this test. Now, I know you'll have one. You'll be holding it in your hand, but I'm going to ask you not to use it because your calculator is going to give you answers that most likely are decimals. But I'm not going to want decimal answers. I'm going to want exact values. Now, I know some of you think that decimals are exact, but they're not. They're just decimal, literally. Decimals are approximations unless they terminate or repeat. So most of your answers are going to have weird things in them like root 3s and root 2s and root 6s. And those things can't, your calculator's not going to be able to show you that stuff. Not to mention I'm going to want to be able to see a process depending on the test that I give. So I don't want to call this cosine of 75 because I don't know what the cosine of 75 is. It's not on the unit circle. So here's what I'm going to do. I'm going to pull out my identity. Now you have a cosine of alpha minus beta identity. And your cosine, I'm going to bring it down and write it up here. Your cosine of alpha minus beta identity tells you to take the cosine of the first angle times the cosine of the second angle. Ignore the negative, just look at the two angles. And then change that negative to a plus, and then to take the sine of the first angle times the sine of the second angle. And that's how you simplify this. Doesn't look simpler, but watch what happens. So here, I'm going to rewrite this as the cosine of the first angle times the cosine of the second. I'm going to change the negative to a plus, and then I'm going to go sine of the first angle times the sine of the second angle. All right? Now, that's not 75. I know these values from the unit circle. I can go to 120 degrees on my unit circle, which if you recall, or if you're looking at the unit circle, remember 120 is kind of right there, just past 90. And to get there, I got to go left a little, up a lot. Well, left is the x value. So the cosine of 120 is the x value, negative 1/2. But sine of 120 is the y value, which is square root of 3 over 2. All right? Now, don't make the mistake of writing cosine of negative 1/2. It's the cosine of 120 that's negative 1/2. The cosine's gone now. Sine of 120, square root of 3 over 2. Sine's gone now. All right? Now, then I go to 45 degrees. 45, as you know, is there. To get to 45, these two sides match. So that's over the same as I'm going up. Root 2 over 2, root 2 over 2. So the cosine is the x, root 2 over 2, and the sine is the y of 45, another root 2 over 2. And then I've got everything replaced, right? So all I have to do now is multiply. So this times this gives me negative 1 times root 2 is negative root 2 over the quantity 4. And this is positive root 6 over the because that's a 3 right there, and that's a 2, over the quantity 4. And I can now have a common denominator, and I could write this as negative root 2 plus root 6, but it kind of looks better to me going positive root 6 minus root 2. Just looks a little prettier, but it's fine either way. All right? Now, you type this in your calculator, and it's going to spit out some terrible decimal. So when I ask you for exact values, if you give me a decimal answer, you're just going to miss this because this is exact, okay? All right, so let's look at this one. This one is not an alpha minus beta. I put this intentionally because this is what happens if you accidentally or erroneously distribute the cosine in. If I distribute the cosine in, which is not right, you end up with something like this. And if you look at this, this is negative 1/2. I know that because I just did it over here. Cosine of 45 is root 2 over 2. And if I subtract these, I get negative 1 minus root 2 over 2. And you can see this value and this value are not the same. So please don't make the mistake of ever distributing a cosine in to these two angles. That is not the identity. You have to use these identities that you're given for alpha minus beta or alpha plus beta. All right, so I will say this too. You're normally not given this kind of situation. You're normally given something like in number 3 or 4. Now in number 3, you look at 75, and really that's the same thing as I had in number 1. 120 minus 45 was 75, but you don't know what sine of 75 is, right? And you can't answer that exactly because even though I type it in my calculator, I'll get a decimal. I want to know exactly what it is, right? So to do that, I'm like, well, are there any two angles on the unit circle that either add or subtract to give me 75? And the answer to that are lots of them. Okay, for example, 45 and 30 degrees add to give me 75. How about 120 minus 45 degrees? That ends up giving me 75 degrees. I'm not going to go through any more, but there are lots of different combinations that when you add or subtract them, you can get 75 degrees. I usually go with the very first one that pops in my head, which is usually the sum of the two smaller ones. I don't tend to think minus as much. All right. So you can use anything you want to replace that 75, but just pick something. Now, I hear people all the time to go, hey, what about 60 and 15? That works. Well, yeah, 60 and 15 do add to give me 75, but do you know anything about 15 degrees on your unit circle? And the short answer and long answer is no. So I got to make sure that the two angles I pick are actually on the unit circle. And by the way, if there aren't any, like if I had said, what's sine of 70? There are no two angles on the unit circle that I can add together to give me 70. You'll quickly realize that. And if there aren't, then you're done. You just circle it and go, I can't simplify any further, based on what you know in this class. All right, so on this one, I'm going to rewrite this as the sine of, and I'm going to replace 75 with 45 plus 30. Okay, and it doesn't even matter the order. You could write 30 plus 45. If I do that, now I have a sine of an alpha plus beta. Now again, don't change that. Don't distribute the sign in. That's not the sign identity. The sign identity, if you remember, is sine of the first angle times, not sine of the second, but cosine of the second. And then you keep the plus, unlike the cosine function where you change it. And then you go cosine of the first angle times the sine of the second. Right? So sine of the first, cosine of the second, plus cosine of the first, sine of the second. Now I have people that go, can't you just go sine, cosine, and put that in front? Guys, it doesn't matter. That multiplication is commutative. You could switch the order right there, but this is the way the identity reads, so this is the way my keys will show up. All right, so now let's go to the unit circle. What do you know about 45 degrees? Well, to get there, you're going over and up the same amount. The sine is the up part, so that's going to be a root 2 over 2. And then here's the cosine of 45. That's the over to the right part, the x part. That's also a root 2 over 2. And then what about 30 degrees? We haven't done 30 yet. 30 is right there. What did I do to get to 30? I went right a lot. So the cosine's the x. That's the amount to the right. That's a root 3 over 2. Make sure you multiply those. Drop down your plus. And then the sine of 30 is up a little. So that's a 1/2. And then like before, you multiply this and get root 6 over 4. You multiply this and get root 2 over 4. And then don't add root 6 and root 2 and get root 8. You know you can't do that. These are like x's and y's. You cannot add unlike radicals together, right? So you put them over the common denominator and you just call it a day. All right? Now, 13 pi over 12 gives a lot of people trouble. And I got a piece of advice for you. The next lesson we have, we're going to learn about half angle identities. And to me, when you're dealing with tangent, it's a lot easier to use a half angle identity than it is to use an alpha plus beta identity. But because we're in the alpha plus beta section, we're just going to go about it this route. Now, I don't know about you, but it's really hard for me to look at that and find two angles on the unit circle that would add to give me that. It's a lot easier to do degrees than it is radians. So because I don't, and that's not a value on my unit circle because I don't have anything on the unit circle that has a 12 in the denominator. So because of that, I'm a little stumped, but I do know something. I can change a radian into a degree using what I call stoichiometry. Now we know that this is a radian value because there's no little degree sign. Sometimes radian values, believe it or not, don't have a pi on them. Okay, like I could say 2 radians. I don't have to say which would be somewhere in the second quadrant. All right, but right here, that is a radian because there's no degree sign. Well, do you know how to, so if that's a radian, how do you change a radian into a degree? Well, you use stoichiometry, right? We know that 180 degrees is the same thing as pi. Well, what that means is, or pi radians, okay? Well, if that's true, what would happen if I divide by pi radians? I get 180 degree equals pi radians. Oh man, you can't see that. All right, one more time. Actually, I'm gonna have to go way back here. We got 13 pi over 12 radians, and I'm trying to change this to a degree. All right, that's what I have right now. So I know right now that 180 degrees is the same thing as pi radians. Well, if I divide both sides by pi radians, then that tells me that 180 degrees over pi radians is equal to 1. Well, that means this is like a conversion factor. I can multiply anything by that and watch what happens. I'm going to multiply by 180 over pi radians, and the radians cancel, and I'm left with degrees. And not only do the radians cancel, the pi's cancel. In fact, I can even divide that 12 in there, and it goes 15 times. And all I have left is 13 times 15 degrees. Okay, that's all I have left is the degree sign, right? And 13 times 15, everybody knows is what, 195? So I have 195 degrees here, right? So that's what I'm going to do. I'm going to change this radian amount to a degrees because to me, it's easier to think in degrees. So here I go. Now that I'm in degrees, that's not a value on the unit circle, is it? No, it goes 180, 210, this is somewhere in the middle. So what I'm gonna do are there any angles on the unit circle that I could add together and give me 195? And with a little bit of thinking, you go, oh yeah, what about like 150 and 45? Or what about 225 minus 30? So I'm gonna use 150 and 45 to replace my 95. And now what do I have? An alpha plus beta identity. Okay, now to me, the alpha plus beta identities for tangent can be the most lengthy ones to simplify, which is why in the future, I'm gonna try, if I can, to use half angles. Now, I won't be able to use a half angle here, but I could have done it here. So at this point, I'm gonna have to pull out my alpha plus beta identity. Now, if you're looking at your identities, you saw that a tangent of an alpha plus beta is the same thing as a tangent of the alpha, the first angle. Keep the sign. Tangent of the second angle, almost looks like you distribute it, but then you're gonna divide it by 1, change the sign to a negative on the bottom, and then just take these two things and write them again, but this time we're gonna be multiplying them together. So I have the tangent 150 plus the tan 45 over the 1 minus tangent 50 times tangent 45. And then here's where it gets ugly. All right, what's the tangent of 150? Okay, so I'm gonna come over here and I'm gonna pull out my unit circle. Here's 150 degrees, okay? And 150, if I map that out here, I'm going left, square root of 3 over 2, and up a half. So the tangent would be the opposite over the adjacent. I can cancel those 2's out, and I'm left with 1 over a negative root 3. And I'm going to bring that negative up, and then I'm going to rationalize, and what do I end up with? Root 3 over 3, but negative. So the tangent of 150 is negative root 3 over 3. Tangent of 45, at 45 degrees, the x and y values were the same. So that's just same over same, which would be 1. And on the bottom, the nice thing is you're going to go 1 minus, and whatever you have for these two, you just put it down here. So minus negative root 3 over 3 times 1. Now I'm going to clean this up, and I'm going to write it over here. So negative root 3 over 3 plus 1 over 1 plus root 3 over 3. Now, these are not the same, right? One's 1 minus that, and one's 1 plus that. Now, I'm going to show you a little hint. You're going to be doing this a lot. Have y'all noticed that anytime you have a fraction over a fraction, the problem looks exceptionally ugly? See, this wasn't a fraction over a fraction. This one right here on the other problem, this looks kind of pretty. It's just a simple fraction, even though there's some radicals. And this has got fractions inside of fractions. Whenever that happens, I'm just going to look at the denominators and find the common denominator of those. So this one has a 3, this one has a 3, so the common denominator is a 3. And I'm going to come in here and I'm going to multiply the top by 3 and the bottom by 3, and I'm going to distribute it in there, and check it out. Look how nicely this cleans up. 3 times this part, the 3's cancel, and then 3 times a positive 1 is just a 3. And then 3 times the positive 1 is just a 3, and then a 3 times that fraction, the 3's cancel, and they leave you plus root 3. And then now it looks better already, but there's one last thing I got to do, and that is rationalize the denominator. Now, if you're looking at this and you're like, I've been on this problem for 10 minutes, I hear you. It's ugly. You're not going to see it. This is probably by far the worst problem to simplify of all the problems you'll see on your test. Okay, so at this point, I'm just going to have to hunker down and FOIL this thing out. So this times this is negative 3 root 3. This times this is positive 3. Be real careful here. This times this is positive 9. And then finally, that times that is negative 3 root 3. Nothing canceled. But here, because these are conjugates, the middle part, right? You're going to do first times first is 9. But what happens with the outer and the inner? They're opposites, they cancel. And then finally, last times last is negative 3. So what does all this clean up to be? Well, I got a 12 right there. I got 2 negative 3 root 3, so negative 6 root 3 and on the bottom I've got a 6, and then couldn't I cancel a 6 in both of those? Like, I could put this over this and get a 2, and that over that and get a root 3 with a negative in the middle, or just think, if I cancel a 6 out of that, and a 6 out of that, and a 6 out of that, what do I have left? 2 minus root 3. And I'm going to do a very similar problem on in a couple of days with a half angle, and you're going to get to hear in like 2 or 3 steps as opposed to 5 million steps that we did right here. So again, worst case scenario, that's what you're looking at here. All right? All right, so let's jump to number 5. This is a new kind of problem. Number 5, they're giving you all this information about, at first it looks a little overwhelming, like, man, why there's so much on the page here? Notice the first thing they did is they said, hey, there's some angle, and by the way, the angle is between 90 and 270. And the angle, when you take the sine of it, it's 3/5. So let's think about that. I'm going to draw a little picture of this and say, all right, if I had an angle that was between 90 that's right here and 270 that's down here, between 90 and 270 would be over here, right? All right. And then if the angle were to exist, it would either have to be in this quadrant or this quadrant. But wait, the opposite over hypotenuse is 3/5. Well, if it's in this quadrant, right, then the opposite over the hypotenuse could totally be 3/5. But if it was in this quadrant, the opposite would have to be -3. It'd have to be going down. So it can't happen here, can it? And by the way, isn't sine positive in these 2 quadrants? All students take classes. Sine can only be positive 3/5 here or here. And it can't be there because it's got to be bigger than the 90 but smaller than the 270. So that means, hey, I got to draw a picture of this angle theta. Angle theta must be right over here in the second quadrant. And while I'm at it, couldn't you use this 3 and 5 and do the Pythagorean theorem and find out that this was a 4, except that you're going left, so -4? Well, check it out. Now, I know everything I need to know about theta right here, except what theta is, which would be nice if I had a calculator, but I'm asking you for exact values. You're going to have to do it a little bit differently. All right, now while I'm at it, I'm going to come over here and think about this beta. Now, the beta angle, it says, occurs somewhere between 0 and 180. So let's think about that for a second. Between 0 and 180, there's 0, there's 180. Bigger than 0 but smaller than 180 would have to put you right here in these 2 quadrants, right? So I definitely can't be down here. But however, cosine of this angle beta that's either over here or over here is negative. Now remember, cosine is defined as adjacent over hypotenuse. And if I draw it here, if I draw this triangle right here, say right there, then think about it. The adjacent would have to be a -1 and the hypotenuse a 4. Is that possible? I can't go -1 to the right. That doesn't make sense. But look, if I draw it over here, draw my angle there and call that beta, right there, then I can go adjacent over hypotenuse. That does make sense, right? Because I'm going left. And by the way, the hypotenuse is always positive because it's the sum of the squares of the other terms squared. So we only go left with negatives and down with negatives. Hypotenuse is always positive. So this tells me because the cosine's negative, but it has to be between here and here, it can't be there, it must be over here. So there's my angle beta, and I could do a little Pythagorean theorem and find out that this was root 17. And if you're not seeing that, remember, we'll call it y squared plus x squared equals r squared. And if, root 15. Sorry, that's a root 15. If I do the math on that, I get 16 here. This is +1. If I subtract that over, I get y equals root 15. Are you with me on that? So this must be up, so positive root 15. And again, it can't occur down here because it's got to be between 0 and 180. So what this means is now I have a triangle that represents theta and a triangle that represents beta. Now let's go to the question in play. Sine of alpha minus beta. Now ask yourself, do you know alpha? No. Now I know it's somewhere over here, but I don't know the exact value. Do you know beta? No. I know a lot about it because I know a lot about the triangle, but do I know the actual angle? No. If I don't know the 2 angles, can I subtract them? No. And if I can't subtract them, can I take the sine of them? No. So what do? Well, I'll tell you what you do. You pull out your sine of alpha minus beta and your sine of theta minus beta formula. And when you subtract 2 angles, remember your formula? Sine of the first you don't have to have parentheses. I'll tell you what, I'm just going to start over without parentheses. All right, you have the sine of the first angle times the cosine of the second angle, and then you keep the negative, you don't change it. Then you have the cosine of the first angle and the sine of the second angle. And the beautiful thing about this is, I don't know the angles, but I do know what the sine of the angle is. So unlike the one we did earlier where we knew the angles and we went to the unit circle and used those values, I don't know the angle, so I have to go to the triangle to figure it out. What is the sine of that angle? 3/5. Now that part you should know because they gave that to you in the original problem, right? It's right here. But what is the cosine of the beta? Well, let's come over here. What's the cosine of this beta? Cosine, they gave that to you, adjacent over that. I can replace that with a -1/4. You might, why did I do all this work then? Well, you did it for these two. What's the cosine of this theta? The cosine of it's the adjacent over hypotenuse, -4/5. And what's the sine of this beta? The sine of it is √15/4. So now that I've got all these values plugged in there, I can now simplify. And by the way, don't cancel the 4's out because then you're not going to have a common denominator, right? If you do that, right? Then you got to have a common denominator to get these added, so don't bother even canceling. So I get -3 on the top over 20. These two negatives cancel, and I get +4√15/20. And then, of course, we can add these two things together and get -3 plus 4√15, all of it over 20, or even better, 4√15 minus 3, all of that over 20. Of course, both of them are correct. Just go what you feel most comfortable with, but you probably will see something like that in a multiple choice test bank. All right? So again, you're going to see more of this tonight on homework, things like that. So again, when you see this kind of information, you're using it to make a triangle. And guys, it's really important that you don't just do this. I see people all the time that go right here and they go, oh yeah, make a triangle. And they go opposite hypotenuse 4. And how does that hurt you? Because you didn't think about where it was. You wrote down +4 because it's a 3, 4, 5 triangle, and you didn't notice that it was really a -4 because where it occurred was a big deal. So make sure you draw a picture, not just of the triangle, but of the triangle in the correct quadrant that fits the information. And that way you can make sure you have your negatives in the right spot. All right? We'll do these again as we move through this chapter. So that is number 5. Let's move on to number 6. This is a different kind of question. Number 6, I give you something with all these angles already plugged in there. Now the temptation is to go, hey, what's cosine of 30? Oh, it's √3/2. What's sine of 30? 1/2. And then you still have this big mess because I don't know the trig functions of 230. Okay, and you ignored the question which says use the sum and difference identities to write the expression as either the sine or the cosine of or the tangent of an angle, unless it goes even further. And I don't want this to be sine of 230 times √3/2 minus cosine of 230 times 1/2. That's not very pretty. So, do you recognize this identity? Sine of one angle, cosine of the other. Cosine of that first angle, sine of the other, with a minus. To me, that looks like a sine of alpha minus beta identity. And the alpha would be the first angle, and that would be the second. See how those two, first, second. So I'm going to write this as the sine of the 230 minus the 30, which simplifies to sine of 200 degrees. Right? And the question was, use these sum and difference identities to write the expression as the sine of an angle. Well, I did that. And because 200 degrees is not on my unit circle, and because I can't for the life of me come up with two angles that are on the unit circle that add together that give me that, I got to stop. And don't say stuff like, what about 150 and 50? Is 50 on the unit circle? No. So if you can't find two that actually work for you, then you got to stop. All right, look at number 7. Does that look familiar? See, when I see this, I see tangent of alpha minus tangent of beta over 1 plus tangent of alpha times tan beta. Do you see it? And I know that this is the tangent of alpha minus beta identity, where the alpha was the first angle and the beta was the second angle. So that means since this right here looks like this right here, all of this must be equal to the tangent of alpha minus beta, right? Which means this is tangent of 60. And I would stop there, except that, wait, I recognize, dadgummit. So I see, my bad, guys. So right here, this is tangent alpha minus tangent beta over 1 plus tangent alpha times tangent beta. See how that's the same thing? So if that's equal to the tangent of alpha minus beta, which it is, that's an identity we have from today, that means all I have to do is plug these two angles in for my alpha and betas. So I'm plugging them in for my alpha and beta, and I get it simplified. Now, normally I'd stop there, but that is a unit circle value. So I'm going to go to 60, and tangent means y over x. I'm going to take the y value, which was up a lot, root 3 over 2, put it over the x value, which is over a little, 1/2. I can cancel the 2's out, and I get root 3, positive. All right? All right, so look at number 8. Number 8, I see cosine of two different angles plus sine of two different angles. But they match here and here, and they match here and here, which has been a common theme. Well, do you have a trig identity that goes cosine alpha, cosine beta plus sine alpha, sine beta? And the answer is you do. It's one of your cosine identities. Except remember, on the cosine of alpha something beta, you switch the sign in the middle. So if it's plus here, it must have come from a minus there. So if that's my identity, I'm going to say cosine of the 230 minus the 20. And we know that that's cosine of 210. And cosine of 210 is actually on my unit circle, right? We know that 210 is right there. And if the cosine is the x value, I'm going left a lot and down a little to get there, and cosine's x, so left a lot. All right? And there's your negative root 3. Okay, now, I actually kind of messed up on this 9 and 10, so I'm going to go back in time and talk about this again. I kept writing out the work, and it was showing up off the screen, and I want you to be able to see this clearly. So you can see I'm kind of covering up my math here, the old math, but anyway. So right here on number 9 and 10, this is number 9, this is a whole lot like the number 5 that we did earlier, but I just kind of want to run through them again. The big difference is I'm just introducing some different trig functions in here to show you that they don't all have to be matching or anything like this. I can put in tangents or secants or whatever. Okay, so right here, remember what we did before? We want to use this cosine of alpha plus beta or x plus y identity, which I do know. It's cosine minus sine of the two angles. However, I got to find a way to break this down and understand just everything I need to know about angle x. Now, so I'm going to have to draw a picture like I did before. And again, this angle is between 90 and 270. And if that's 90 and that's 270, bigger than 90 sends me that way. Smaller than 270 sends me that way, which means this angle right here, angle x, has to be somewhere in here. Okay? Can't be anywhere there or anywhere there. But also, tangent has to be negative. And we should know at this point, after a lot of work, that what do we know about tangent and being negative? Well, we know that all students take classes, so I'm positive with tangent in the first and the third. I must be negative in the second and the fourth. So the only place for tangent to be negative, but also for this angle to occur, would be here in the second quadrant, which means I know it's not there. So all I'm going to do at this point is draw some fictitious angle. I don't know exactly which way to draw it, but that's going to stand for my angle x right here. And I know sometimes it gets confusing once I start putting x's and y's for angles instead of sides, but this represents an angle like a theta. And here's my triangle right there, right? And I know that the tangent of this angle right here is opposite, which is either 4 or negative 4. I'm going to put a 4 for now, over adjacent, which is either 9 or negative 9. And if you look at this, the only really way it makes sense is for that to be a negative 9 because I'm going left, because that's a positive 4 up. All right? And if I want to know the hypotenuse, which I am going to have to know later, I'm guessing, I'm going to have to pull out the Pythagorean identities, my Pythagorean theorem, and say, all right, to find that hypotenuse of that r value, I got to take this 16, and I got to take that 81, and I'm going to have to square root this 97 to get my r value. Okay, so hopefully I haven't made any careless math errors here, but that's a root 97. All right, right here. All right, so I know everything I need to know about this except the actual angle itself. But again, if I want an exact value, I don't want that approximate value of that angle, which is what my calculator would probably tell me if I pulled out my trig functions. All right, now I'm going to figure out about angle y. Now, I know that angle y is between the 180 and the 360, greater than the 180, but smaller than the 360. So I know it's over here in the third or the fourth, so it can't be there. I also know that angle y, if I cosine the angle, I get a positive 2/3. Well, where is cosine positive? All students take classes over here. So it's positive in the first and the fourth, but so it can't exist here. We know it can't exist in the first and second. So it must be somewhere in this quadrant, this angle y. I can label it there or whatever. All right, so if that's my angle, and I could think about it as I can't think about it as a negative angle because again, negative would not be bigger than 180. It has to be something like, I don't know, 300 or 290 or something like that. So, but what I can do is I can label the triangle that goes with that angle y. So what do I know about it? I know the cosine of it is the adjacent side over the hypotenuse. Well, that makes sense. Look, adjacent over hypotenuse, they're both positive. And then I could do, again, 2 squared plus the y squared equals the 3 squared. 2 squared plus y squared equals 3 squared. And with the little Pythagorean theorem, I take this 9, subtract the 4, and get a 5. So we know that y is either plus or minus root 5. And you tell me, is it positive or negative root 5 if it's going down? I'm going with negative root 5. All right, so now that I have my two triangles, I should be able to answer any questions that arise from me doing this. So what do you know about cosine of x plus y? What do you know? Well, I know that the cosine of the first angle times the cosine of the second angle minus sine of the first angle times sine of the second. I know that that is what it's equal to. And now I know everything I need to know about angle x and angle y, so let's find the cosine of it. What's the cosine of angle x? It's negative 9 over root 97. I'm going to jump over to the right side. What's the sine of angle x? It's 4 over root 97. All right, what's the cosine of angle y? It's 2/3, and they actually gave you that value if you recall. And what's the sine of angle y? The sine of angle y is negative root 5 over the 2. Are you with me? So I've got adjacent over hypotenuse. I've got adjacent over hypotenuse. And then here I've got opposite over hypotenuse. And then here I've got opposite over oh, dang it. See, I'm glad I double checked. Negative root 5 over the 3. That's the hypotenuse. And as you've seen before, there's your common denominator. So I don't want to cancel that 9 and that 3 out because then I won't have a common denominator. So I'm just going to write it as negative 18. Here I get positive 4 root 5. And all of this is over 3 root 97. And for those of you that are cussing me right now and going, really? Now you got to rationalize? My short answer to you is yes. But my better answer to you is I do a much better job on tests of avoiding numbers like this and using Pythagorean triples, or at least at the very minimum, better looking radicals than that guy right there. So don't worry too much about it. But remember, you have a calculator. So even if you did have to do this, that times that is negative 18 root 97. And then this times this is just 4 root whatever the 5 and the 97 is, which you could multiply 5 and the 97 without too much trouble and get that. And on the bottom, you end up with a regular 97 times a 3. And again, that too on your calculator is not going to be that big of a deal. So I will definitely avoid nasty numbers like this on your test. So don't worry about that. But I just wanted to show you the process here. Okay? And then after that 9, I want to come down here and finally do number 10. Number 10 says, find all the solutions of the equation in that interval. Okay, so we're solving this thing. And I'm looking at it going, what the heck? That's a lot worse than I'm used to seeing when I saw those solved problems on my last quiz. Okay, so now they did tell me that the answer is between 0 and 2 pi. So that tells me you have to write your answers in radians. Okay, so don't go changing everything to degrees if it says leave it in radians. But you know what I recognize from this? I've got an alpha plus beta. I've got 2 angles added and 2 angles subtracted. Right? So since I do have 2 angles added and 2 angles subtracted, granted I don't know what that angle is, I can use my alpha plus beta and my alpha minus beta identities. So first, let's use the sine of alpha plus beta, which is the sine of the first angle times the cosine of the second. Keep the plus, and then you have, so all of this is going right here. Then you have cosine of the first angle and the sine of the second. And then I'm going to bring down this plus sign right here. And then I'm going to take this and put it over here. So I got this one right there, brought over the plus. Now I'm going to do this one. Well, this is an alpha minus beta for sine. So again, sine of the first, cosine of the second. Then take the negative, and then cosine of the first, sine of the second. And all that's equal to 1. Now look at my answer. Can you clean this up at all? Sure, because right here, these two things are exactly the same, but with opposite signs, so they cancel. And then what do I have left? I have 2 of those. It's like saying xy plus xy is 2xy. Sine x cosine pi root 3, sine x cosine pi root 3 is the same thing as 2 sine x cosine pi root 3. And again, it's all equal to 1, right? So bring over your 1. Now, you could have simplified this earlier, but who knows what cosine of pi over 3 is? Well, you think about that with the unit circle. Pi over 3 is up there. So what's the cosine to get up there? It's over a little. So all of that is 1/2. I don't know what sine x is. That's a 2. And what do I have at this point? Well, that 2 cancels with that 2. And all you have left is the sine of x equals 1. Now, at this point, you have sine of x equals 1. Now, I could pull out my calculator and do an inverse sine problem, right? And I'd do inverse sine, and I would get 90 degrees. But here's the thing. I can do this on the unit circle. Sine of what angle? Think about it. You have this unit circle, right? Sine of what angle has a y value of 1? That's straight up. This is a negative 1. These are all other unit circle values. The y value might be 1/2, might be root 2 over 2, might be square root of 3 over 2, depending on the angle, right? But the only time where the sine of the angle is 1 would be where the y value is 1. Well, that occurs right here, right? The y value is 1. So the only value for x that actually works here is pi over 2. And again, don't say 90 degrees when it says leave your answers in radians. All right? Well, guys, you're going to see some homework questions like this. Do the best you can. We're going to be doing more and more with these, a lot more practice out there. Remember, you have your identities in front of you. Hopefully, you'll be in good shape. Please ask questions if you have trouble. All right, good luck, guys.